This is a video about torque on a loop. Normally this is a topic that's easy to kind of back into. For this time I want to try this in the forward direction. So if I have a loop of wire, and I'm going to start with just a rectangle. If I have a loop of wire and it's carrying a current, maybe clockwise, and let's give this wire some dimensions. We will give this a length well, we can just give it a length of L, and we'll call this a height of H. We're going to stick this thing in a magnetic field, and let's have the magnetic field run this way. So a couple of things are going to happen, and to get this I would like to start by just numbering the sides of this wire. 1, 2, 3, 4. I'm going to look at each side individually. Looking at side number 1, I have a current going upward. I have a magnetic field going to the right. So what I end up with is a magnetic force that points into the screen. If you're not completely convinced, take a second and right hand rule that thing, you'll see it. On segment 2, my magnetic field and my current point in the same direction as each other, so I get no force. On segment 3, current points down. My magnetic field points to the right, so I get a magnetic force that comes out of the screen. And on segment 4, current goes left, B field goes right, so I get a force of 0. So segments 1 and 3 are getting a non-zero force. Segments 2 and 4 are getting 0. I want to look at just what these magnitudes are. This force over here is going to get a strength of I times the length of this segment, which is H, times B. Same story over here. I'm going to get a force that is I times H times B. This force points into the screen, this force comes out of the screen, so those are opposite directions. In total, the total force on this loop is 0. That isn't exciting enough to merit its own video. There must be something else going on. A total force being 0 means the center of mass of the system is inertial, meaning if it's moving already, it's going to keep moving in that same way. If it's not moving yet, it's not going to move. If we start with this thing being stationary, then we can say the center of mass of the system is stationary. The center of mass of the system is right here. There's the center of mass. There's not actually any mass at that location, but that's okay. I'm going to erase some of these extra things because this picture is getting really busy. I'm going to erase a couple of labels and these numbers. Okay, a little bit less going on. Over here on the left side of this thing, I have a force of IHB that points into the screen. Now that force is not pointing on the center of mass, is not acting on the center of mass of the system, it's acting a distance away from it. It's actually acting at a distance of L over 2 from the center of mass. And if it's acting at a distance of L over 2 and it's perpendicular to that separation distance, that means that we are getting a torque here. So the torque on segment 1, if you remember, torque is a perpendicular force times the distance. So I'm going to get my force times the distance, which was L over 2. So I get FB, which is IHB times L over 2. There's my torque. Over here, I get the same thing. The torque on segment 3 is going to be IHBL over 2. Exactly the same reason. This torque over here will make this side of my wheel, side of my loop, rotate backwards into the screen. If I were able to view this thing from above, so I'm going to look from right here. If I were able to view this thing from above, I would say here's my center of mass, and this side is getting a force that points back into the screen. There's my force. So that was a torque. Over here on this side, I get a force that points this way. So in both of these cases, I'm getting a torque that wants to rotate this bar. Which means the total torque on this system is not 0. The total torque on this system is actually going to be the sum of these. So I'm going to get an IHLB over 2 plus IHLB over 2, which means I get an IHLB. Not quite done. Over here in the middle of this formula, I have this H times L. H times L looks a lot like an area, and it is. So I'm going to get a total torque on this loop that is I times the area of the loop times B. The reason that I'm writing it this way, I worked this thing out for a rectangular loop. If I were working this out for a circular loop, it turns out that I would get the same result. So I've still got this area, just then my area is going to be a pi r squared instead. It's nice to develop this with a rectangle, just because it's a little bit cleaner. Now there's one more thing. This whole thing is for one loop of wire. I could take this thing and wrap it around, right? Once, twice, 3, 4, 5, whatever, and we call those turns of wire. So if I wrap this thing around 5 times, I'm going to get 5 times as much torque. So I want to multiply this by n, where n is my number of turns. But that is my formula for the torque on a loop.